Okay, so I want to go through a quick little example here. I mean, it may not be that quick, but I'll try to keep it quick on how a secant line, so how 2 points, or how the line between 2 points can be used to allow us to determine the slope at a given point. Now we've calculated the slope a fair bit in the past, and you recognize that you do need to have 2 points in order to do that. But what we'll see is what happens as our points get close together and it essentially approximate a single tangent to the curve and basically and allow us to determine what the slope of that tangent will be. So pretty simple setup here. The blue curve is the quadratic 1/4 x squared. I have 2 points A and B, and A is actually the x value of this point and B is the x value of this point. And then of course my little formula here is calculating slope. F at B is the y value at B, F at A is the y value at A. So I have y2 minus y1 over x2 minus x1 essentially here, and that of course is slope. Now what you'll notice is as I move this point, my slope is changing. As I get close to this point, so essentially as my points get close to being the same point, my slope is going to approach a specific value. Now I want to keep this at 3 to make it easier. And if I can do a good job here of sliding this along, you can see I think that my slope is getting closer and closer and closer to 1.5 until the point where the 2 points are on top of each other and my slope is undefined. Now again, you can sort of see that the red lines disappeared as well, and I think that makes sense if we think about I have 2 points now. I'm trying to subtract their y values, so y2 minus y1, given the fact that the x values are the same, will be a value of 0. So I have a numerator of 0. My denominator though is 3 minus 3, and much more obvious, that's going to be 0 as well. And so I'm dividing by 0, and of course that means my slope will be undefined. Let's grab the b value, and just if I continue on past that point, you can sort of see that my slopes are getting smaller, and then again as I approach that b value of 3, my slope once again is approaching. There's 1.4, 1.4, 1.425, and again goes through that 1.5. And so I think it's pretty safe to say that as my points get closer together here, my slope is approaching the value 1.5. It never actually is 1.5 because it's slightly below or slightly above, and the 1.5, or sort of where the 1.5 would be, is undefined. But the basic idea of what I'm moving towards is that as this gap between the points closes, as the points get closer and closer together, my slope is approaching 1.5. Okay, now switch this up a little bit. You may not be able to tell right away. I still have my 2 points, 6.5 in this case, and the x value of 6.5 and the x value of 3. But what I'm displaying off to the side here is slightly different. Now a hasn't changed, a is still the 3, but I'm displaying this value h, which represents, hopefully you can see, the gap between the 2 points. So that as h changes, this point is approaching the 3 again. Now, I think you can see that nothing has changed. I'm taking f of a plus h, so f of a plus h, which is of course our old b value. You plug the b value into your function and you get whatever the y value used to be. The a value, of course, f at a has not changed at all. My denominator though is h by itself, so this 2.76, which is, as it was before, 5.76 minus 3, or the b value minus the a value. Okay, so hopefully you can sort of trust, and if you can't see it right away, that this is just another way to rewrite the exact same formula. I'm displaying this value h, which is actually the space between the 2 points instead of the actual values of the 2 points. but which will end up being the exact same thing in the long run. And again, you can sort of see as this h value approaches, as the points get closer together, as the h value approaches 0, the slope is once again approaching that same value of 1.5. This one's a little bit more accurate than the last one was. So I can get close to it, getting close to the 1.5, getting really close to the 1.5, and then right at that 0 value, I'm undefined, just beyond, again, close to 1.5, but on the other side. So, the obvious question, what does that mean in terms of the math that we're actually going to be doing? Well, again, this is our original slope formula back to grade 9, y2 minus y1, so the change in the y direction divided by x2 minus x1, the change in the x direction, the rise over the run. So now this is just a variation of that same equation. If our x values are b and a respectively, then our y values are f at b and f at a respectively. So again, the equation here now is exactly the same as it was here, with just a substitution of b for x2, a for x1. And then if we think of b minus a, think of h as being the gap between b and a, so b minus a being the same as h, then we can determine that the value of b is a plus h. The value of a, of course, is still a. And so this once again becomes just another variation of that same slope formula. If we know a and we know the gap between a and another point, we can calculate the y values, we can divide by the change in the x values, and we can determine the slope of a secant between 2 points that are fairly close together. And then the extreme of this, what if we can get to the situation where the gap between our points becomes so small that it's essentially a gap of 0? And that's where we sort of deal with this idea of a limit. The limit is just the value that we're approaching, again, as our gap between our 2 points gets really close to 0. We know that it can never actually get to 0, but as we saw on the demonstration in Desmos, as it gets close to 0 from either side, the same value is what we're approaching. It was 1.5 in the example. We'll be determining what it is depending on the question moving forward. And just a quick note that we may see this same formula in basically this form, but with an x instead of the a. Typically we use the a when we know the value, when we're looking for the slope at point x equals 2. And then we use this in a more general sense when we're looking for a generalized equation for slope that we could then plug numbers into at a later date. So, I'm going to go with one example here. And essentially the question says find the slope of this at the point x equals negative 2. And the slope formula that we'll use is the limit one. Okay, so again, recognizing that this is the y value that is a point a little bit away from our x value that we're interested in. This is the y value at x equals negative 2, and h is the gap between the two x values. And so a little note off to the side, a is negative 2, f at a is equal to f at negative 2, and if we calculate that value, negative 2 in here squared is positive 4. 2 times negative 2 will be negative 4, and minus 3 gives me a value of negative 3. So when I go to plug this into the formula, we're asked to put the negative 2 in for a, so it's f at negative 2 plus h minus f at negative 2 divided by h. The limit part of this will only come into play at the very end of the question, so we don't have to worry about it for now. We're now simplifying this. Well, to do that, of course, we'll need to know the actual equations. The equation was from the top, x squared plus 2x minus 3. So this gets substituted in for the x in the first term, plus 2 times substituted in for the x in the second term, minus 3, and then minus f negative 2, which was a value of negative 3. Expand the first term, multiply the 2 here through the negative 2 plus h, and as we simplify that numerator, we'll see that we have a 4 minus 4 minus 3 plus 3, so all the units are gone. I'm left with an h squared and a minus 2h, negative 4h plus 2 more h. And as we were seeing in the work earlier, the h should factor out of the top and then divide through with the h on the bottom. And now this is where we'll sort of go with that one extra step. So what the question's really asking me here is, what is the slope as h approaches 0? The limit is just telling us again that we can't really find that value, but we know that that's what we're approaching. So the limit itself doesn't really come into play here, except that it makes this statement mathematically correct. I can't substitute a 0 in here, except in the context that I understand I'm really looking for the limit. What is the value that we're approaching, not what is the actual value at that point. And so once the h's have divided out here, I can put the 0 in just for the sake of finding out what the slope is at that point, and I find that the slope at that point would be negative 2.